Okay, hello everyone. Nice to talk to you all. So this class we're going to continue our topics on the fundamentals of environmental engineering and science. And specifically, this class we're going to talk about the hardness of water. So first, let's do a recap of our last class. So basically, last class we did a brief overview of the water treatment methods. As you can see, it includes a lot of processes. For example, we can use screening to remove larger objects before we process the water quality, right? And we use a specific step that's called coagulation, flocculation, and clarification to remove the colloids in the water. And the reason why we saw those colloids, or why the colloids are stable, is because of three reasons. First, the particles that's composing these colloids are very small. So it's going to take a very long time for them to settle down based on their gravity. And secondly, typically these particles will carry the same type of charge, which is negative charge. And as I mentioned briefly, this negative charge is actually caused by the silicon dioxide that's existing in these particles. And furthermore, the Brownian motion of these particles will move these particles around, so it's going to be more difficult for them to collide together and form larger particles. And the method we use is to introduce coagulants into the water so that we can form larger particles, and we call them as flocks. And specifically, we actually use these trivalent ions, which includes aluminum or ferric ions, right? And then after these coagulants are introduced into the water, we need to go through a rapid mixing so that the coagulants can well disperse in the water, and then they can start to neutralize the surface charge or neutralize the charge that's acting on these particles so that they can form larger flocks. So one thing that I forgot to mention is that for this rapid mixing process, typically we will design a reactor that should have the correct volume of it. So to calculate this volume, it is actually quite straightforward. So what we just need to do is to multiply this retention time, which is typically the time that the water is going to stay in this reactor, multiply that by the flow rate that we're going to process. So as you can see, the flow rate typically has a unit of meter cubed per second, right? And then the time will have a unit of second. So if we multiply these together, that's going to have a unit of volume. And this volume is actually the volume of reactor. Okay? So the same happens for the flocculation. So as I've introduced, during the flocculation, we will use a slower mixing. This is mainly because we don't want to break those larger flocks, but we still want some type of mixing. This is to let the water to more or particles to distribute more homogeneously, and also we want these particles to move around so that they can collide with each other and form larger particles. But if we increase this mixing speed by too much, then the water is going to create some shear force on these larger flocks, so they're going to resuspend the particles or break these particles apart, right? And because of that, we're going to use a smaller velocity gradient. So if you compare the velocity gradient for the rapid mixing is 700 to 1000 per second, right? Well, for the flocculators, they will use a relatively slower or smaller velocity gradient. And at the same time, we're going to use a longer residence time because this flocculation is because of the slower mixing, the particles are going to take longer time to form larger particles, and they're also going to take longer time to settle down. So that's why we're going to use a longer time for the processing of the water during flocculation. And because of that, when we design the volume of the flocculator, we should use the same method, right? So you should notice that the flow rate here has to be equal to the flow rate here. This is mainly because the water flow rate that's going to a water treatment facility is always the same, right? And then if we multiply by this longer time, this simply means that the flocculators normally will occupy a much larger space to process the water. So this is for the paddle flocculators. So paddle flocculators composed of these paddles. So these paddles will move around, right, rotate, and then this will mix the water more homogeneously. So there are also baffled channels. For these baffled channels, there are no revolving objects. So what happens is that the water will just flow around in the channels of this of this flocculator, and also it needs a relatively longer retention time. And actually, the speed of the water, or velocity of the water, is also relatively slow. So for a channel flocculator or baffled channels, they typically look like this. So again, here this is showing a paddle flocculator. You can see there are paddles, and then this is going to enhance the mixing of the particles in the water, and also to promote the flocculation, to promote the to growth of the larger particles. Well, for these channel flocculators or hydraulic flocculators, what happens is that we're forming these channels to let the particles or let the water to stay for a longer time within these channels. So if we could have a longer retention time, then the particles can form to a larger volume, and they can finally settle down or grow it large enough and then further settle down. Okay, so this this type of flocculator is basically moving from up to down. So this is going to create this gravity potential so that it can move from a higher height to a lower height, right? And we can also use these type of hydraulic flocculators. So what happens is that water is introduced from one side, and then because of this baffle here, it has to move downwards, and then it has to move upwards, downwards, upwards. So we'll go through these zigzags. And so in this way, it can spend a longer time in this flocculator, right? So basically, we want to enhance the retention time of the water in the flocculator so that we can achieve the goal of the flocculation. All right, so here is a quick quiz here. So compared to the coagulation, a smaller g is used for flocculation. So remember, g here is the velocity gradient, right? So why do we use a smaller g for flocculator? There are two options. A is to destabilize the particles, and B is to prevent the breaking of particles. So as we have introduced, in flocculation, we don't want a rapid mixing because we don't want to break the larger particles so that they can get resuspended. So that's why we're going to use the choice B here. Right? And as you can see, the coagulation, flocculation, and clarification or sedimentation, they can be a series of processes. For example, in the real power plant, it can be different modules to realize these different goals. But actually, for a smaller scale of the water treatment plant, we can actually use these types of upflow solid contact clarifier to achieve the simultaneous or almost simultaneous coagulation, flocculation, or mixing and clarification of the water quality. So what happens is that here we have the influent of the water to be treated introduced into this clarifier, and at the same time, at the top of the clarifier, we're introducing these chemicals or the coagulants. So right after they mix, or at the region where they mix, we're going to use a rapid mixing here, right? Because of this rapid mixing, the coagulants are going to well disperse among the water. And furthermore, as they further move down here, and as you can see, basically this is conical shape that's going to expand the cross-section area of this geometry here. So if we have a larger cross-section area, then the velocity of the water is going to become lower. So what that means is that basically here, the mixing will get reduced. And also for this baffle here, we're going to use a slower speed. So the mixing is becoming more mild. So you can see we introduce the coagulants, and then we use the rapid mixing. And here, the mixing becomes relatively moderate. So this will enhance the flocculation. And then after they travel down here, the larger particles or the flocks can settle down to the bottom, while the cleaner water can move up. And further, we can take these cleaner water and then let them go through the effluent, right? So this is a more centralized or a more compact device to realize the clarification of the water. So that's why if you search for pictures of the drinking water facility, you can typically see these circular setups, right? Actually, these circular setups are the clarifier we're talking about. And it is a very common device to purify the water we need, okay? So that is all about the coagulation, flocculation, and clarification. So you can see that a serious process have to be needed are needed, right? For coagulation, we need to introduce coagulants, and that's going to cause or consumed alkalinity, and further it will reduce the pH of the water. So here, since we talk about chemistry, then we need to mention about another very important process for the drinking water treatment, which is called the softening. Okay, so the softening is widely applied when we need to deal with the groundwater, or if the water is coming from deep wells. And this is mainly because the water from the deep wells or the groundwater are typically relatively clear or clean, which doesn't have or doesn't contain those colloids, or we can just use a simple filter to get rid of those colloids. But what is the main issue for the water is because of the metal ions. So basically, there are a lot of metal ions that includes calcium, magnesium, ferrous, barium, beryllium, and they can form. So basically, when they exist in the water, they can form, for example, for calcium, they can form the salts or the compounds that are soluble in water. But once they're boiled, and they're going to form those scales, right, or sediments. And because of these components, or because of these ions, when we are using soap to wash our hands, and this higher concentration of the metals are not going to foam this soap easily. So this is also another feature of observing whether whether the water is hard or not. Okay. So to calculate the hardness, so basically the hardness is a parameter that evaluates what is the concentration of all of these polyvalent cations. Okay, it can be in the state of +2, it can in the state of +3. So it is a sum of all of these polyvalent cations, which will become sediments when they're being heated. Okay, so as you can see, if we want to calculate this hardness, so this TH here means total hardness. We cannot directly add all of these mass concentrations together because they're not dealing with the same type of species, right? So basically, this represents how much of carbonate solids is going to form after they are being heated, right? So we have to convert them into mole fraction or equivalent fraction. So again, or equivalent concentration. So again, we're dealing with this equivalent concentration again, or normality, right? And more commonly, people will use the equivalent mass concentration, which is to show this concentration in milligram per liter of calcium as calcium carbonate. Okay, so here I have a few images of how the hardness or hard water can affect our daily life. For example, for the pipes that are transporting this water, once they form these scales or sediments, they can just get attached onto the wall here. And as you imagine, if we're pushing through the same amount of water here, the smaller cross-section area simply means that the velocity of the water will become much higher. And a higher velocity will mean a much higher pressure drop. So basically, the pumping power have to be much higher in order to obtain the same amount of water. So this can basically affect how the household or residential people can use their water. And also, actually, the power plant, and especially the coal-fired power plant, are quite concerned if the water they receive is hard. This is mainly because for a coal boiler, there are a lot of these tubes that contains water, right? So the coal particles will burn, right? Generates a lot of heat. The heat are going to evaporate the water into the gas phase, and these high temperature gas are going to drive the turbine and generate electricity. So here, we really don't want any metal ions or polyvalent ion to exist in water, because once they are heated, if we if they form these scales or sediments in the tube, then that's going to block the water being transported here, right? And in that case, there's no way they can generate the same amount of steam to drive the turbine, and that's going to significantly influence the performance of the power plant. So if you search for power plant and let's say search for the conditions for operating a power plant, there's always requirements on how hard the water they can use, or requirements on the concentrations of these polyvalent cations in the water they use. Okay, so once we know this equation, how can we calculate the total hardness? So here I have a simple example here. So basically it is showing that we have a water sample that's taken from certain well in Illinois, okay? And here basically it's a table that's containing the concentration of all different types of ions and with their specific concentrations. So you can see the specific concentration are also shown in milligram per liter, right? As we have introduced, to calculate the total hardness, we cannot add all of these mass together because different types of ions will have different mass. And so there's no, it isn't a uniform quantification of how hard the water is, right? So we can first calculate, or basically we can convert these mass concentrations into equivalent mass concentrations of calcium carbonate. But the first step we should do is to convert these mass concentrations into equivalent concentrations. So what we can do is that we can first identify all of these polyvalent ions, right? So you can see that there is ferrous ion, right? So the ferrous ion is basically the iron that's in the 2+ state, right? So the concentration of the iron, we can basically list a table here. So first we can, in the first column, we can put in the mass concentration, which is milligram per liter. All right. And we see that for the ferrous ion, this is 0.2. And what else? Are there other types of ions that can contribute to the alkalinity, right? So contribute to the hardness. So as we see, they should be all of these polyvalent ions, right? So the manganese is polyvalent, right? But the concentration is 0, so we can just ignore the manganese here. And then the ammonium, right? Ammonium is not a polyvalent ion, right? This is just +1, so we don't need to consider about that. Sodium, no. Potassium, no. Calcium, we need to consider about that. Calcium is 2+. Let's just write the mass concentrations in here, 67.2. And then magnesium, right? This is 40.0. And barium. So barium is also going to contribute to the hardness, right? This is 0.5. Okay. So then, how can we calculate the equivalent concentration? So to finally calculate the equivalent mass concentration of calcium carbonate, we need to first calculate what is the normality, right? So what is the normality? But to calculate the normality, we need to first know what is the equivalent weight, because we need to divide the mass concentration by the equivalent weight of these specific elements. So first, basically, we need to find out how many hydrogens these species can either accept or release, right? So you can see that for ferrous ion, it corresponds to a number of 2. Calcium is 2. Magnesium is 2. Barium is 2. So this is quite easy here. And then that's going to be the equivalent weight. So the equivalent weight is going to carry a unit of gram per equivalent, right? So equivalent weight is just the molecular weight of these elements divided by the Z here. So for the iron, we know that this is actually 56 divided by 2, right? Calcium is 40 divided by 2. Magnesium, 24 divided by 2. And barium It's 173 divided by 2. Okay, so if you want to calculate that, this is 28, this is 20, this is 12, and this is 86.5. Okay, and then now we can calculate what is the basically what is the normality, or what is the equivalent concentration. So equivalent concentration will carry a unit of equivalent per liter, right? And this is calculated by dividing the mass concentration by the equivalent weight. So that's going to be 0.2 divided by 28, right? 67.2 divided by 20, 40 divided by 12, excuse me, and then 0.5 divided by 86.5. So if you compare these four numbers, you can see that for the ferrous ion and for the barium ion, their equivalent concentration is much smaller compared to calcium and magnesium, right? So later in the calculation, we can just ignore these two terms. So basically, that magnesium and calcium are the most important contributor to the hardness of the water, right? So once we have this equivalent concentration, then we can calculate what is the equivalent mass concentration of the calcium carbonate, right? And as we have mentioned before, that is just the normality multiplied by the equivalent mass of the calcium carbonate, which is 50. So here, basically, we can multiply 67.2 divided by 20, multiply by 50, 40 divided by 12, multiply by 50 again. Okay? So based on the equivalent concentration, we can multiply that by the equivalent mass concentration of the calcium carbonate. And this is going to give us the equivalent mass concentration, right? And then, basically, we can add all of these together. This is basically 67.2 divided by 20 multiplied by 50 plus 40 divided by 12 multiplied by 50. And this is going to give us the value of 335 milligram per liter as what? As calcium carbonate. Okay, so this is how we can calculate the total hardness of the water. So one feature that you can find is that basically the most important contributor of the hardness is actually coming from calcium and magnesium. And this is actually the case for most of the water we're going to deal with. Okay, so this is the reason why we can just use the calcium and magnesium concentrations to calculate what is the total hardness. And typically, for the water treatment plant, it just needs to treat the water or soften the water so that the hardness is between 60 to 120 milligram per liter as calcium carbonate. And this is how we can calculate the total hardness of the water. And then, as a matter of fact, the hardness can further be divided into different compositions. So as we have introduced earlier, for a water sample there can be concentrations of all different types of ions, right? And these are basically cations. There can be calcium. So I'm using a bar chart to represent what is the concentration of the calcium, right? So for the cations, let's say there can be calcium ions, magnesium ions, let's say ferric ions, or ferrous ions, so on and so forth, right? So each length of this bar represents or is linearly correlated with the concentration of these cations. So there can also be anions, right? So we introduced that basically in the water, if it's a buffer system, there must be some bicarbonate ions. And as a matter of fact, because these species typically have a lower solubility with the carbonate, so actually a lot of these anions are composed of the bicarbonate ions, right? Because this is soluble. So there can be some carbonate ion. For example, magnesium carbonate is soluble in water, okay? And then some of them can be, let's say, sulfate ions, and some of them can be chloride ions, right? So we should notice that actually the hardness is represented by this higher bar here, okay? So we have also mentioned that for cations, there are not only these polyvalent ions, right? There can also be some sodium ions. There can be a much higher concentration of sodium ions. There can be ammonia or ammonium ions, right? And also maybe here there can be some other more types of ions. Okay, so you can see that actually this lens represents the total hardness, or the TH. Well, on the anion side, this lens will represent the carbonate hardness. So basically, these carbonate species are going to contribute to the hardness. So there's a certain fraction of the anion that's contributing to the hardness, right? And then for this species, or for these compositions, and they're called non-carbonate hardness. So why do we care? Why do we further separate that into carbonate or non-carbonate ions? This is mainly because for the carbonate hardness, it is very easy, or it is relatively easy to remove, because we can simply remove these carbonate ions by just introducing lime into water. Okay, we can either introduce calcium oxide or calcium hydroxide into water, so that you can see that basically this will form, or this will help form, the calcium carbonate or magnesium hydroxide, or these iron ferric or ferrous carbonate or hydroxide, so that we can remove these carbonate species, right? But if we, let's say, for example, if we introduce lime into calcium chloride, nothing is going to happen, right? Because we cannot remove these carbonate, we cannot remove these species or non-carbonate hardness with these lime species here. And because of that, we need to introduce some further species, which is the soda. So soda is mainly composed of sodium carbonate, right? By introducing sodium carbonate, we're providing more carbonate into the species. So basically, we're enhancing the carbonate concentration, right? So in that way, it can further react with the calcium chloride to remove these non-carbonate hardness, okay? So you can see that basically this total hardness, so basically this carbonate hardness, there are, if we really want to calculate what is the concentration, what is the carbonate hardness, it is actually based on the relative relationship between the total hardness or the alkalinity. Okay, so this is the total hardness or alkalinity, whichever is smaller. So for example, here, in this example here, we see that this total hardness is actually this long here, while the alkalinity is this long, because alkalinity is contributed by these bicarbonate ion or carbonate ion here, right? So you can see that this carbonate hardness is contributed by this alkalinity here. So under this situation, alkalinity is smaller than total hardness, right? So the alkalinity is equal to the carbonate hardness. So there's another situation. So basically, we can have a lot of these alkalinity here. Okay, well, up here, let's say the hardness is just this long, calcium, magnesium, while the remaining of them are sodium. Okay, so under this situation, you can see that the total hardness is just this long here, right? And we won't use alkalinity as the hardness, simply because the sodium is not contributing to the hardness of water. So remember, the hardness is just contributed by these polyvalent ions, right? And this is the reason why, under this situation, the carbonate hardness is just the total hardness. So that's why to calculate the carbonate hardness, it is the total hardness or alkalinity, whichever is smaller. Okay. So as a matter of fact, this carbonate hardness is mostly contributed by the calcium bicarbonate or magnesium bicarbonate. So basically, you can ignore these carbonate species in there. So they're mostly contributed by these bicarbonate species. Okay, and also this hardness will decrease with increasing temperature, right? Simply because they will just settle down. So the concentration of the hardness or the hardness value is going to decrease. So this is also meaning that these carbonate hardness are temporary hardness, and that's why it's easier to remove from the water. So there can also be non-carbonate hardness. For example, here in this first example here, you can see that basically this region will represent the non-carbonate hardness. Okay, so we have introduced here, simply because these hardness or these metal ions, they're not coupled by these alkalinity species. They're coupled by, let's say, chloride or sulfate ions, and which means that they're going to be permanent hardness, right? For example, they can be calcium or magnesium sulfate or chloride or nitrate. Okay, so therefore, to remove these non-carbonate hardness, we have to introduce more carbonate ions into the water to let them settle down. Okay, so for this case, you can find out that the total hardness is actually equal to the carbonate hardness plus non-carbonate hardness. So what happens here for this second example? All right, so for the second example, are there non-carbonate hardness? No, right? Non-carbonate hardness here will be just equal to 0, because all of these polyvalent ions are coupled with these carbonate species, right? So non-carbonate hardness will equal to 0. So the relationship that the total hardness is equal to carbonate hardness plus non-carbonate hardness still satisfied, simply because the second situation, the NCH or non-carbonate hardness just equal to 0. Okay, so here you can see that I used these bar chart or bar graph to represent the hardness concentration. And theoretically, we should convert all of these iron concentrations into the equivalent mass concentration of the calcium carbonate. Okay, so doing the same thing here to convert them into the equivalent mass concentration of the calcium carbonate. Basically, convert them into milligram per liter of calcium carbonate as calcium carbonate. Okay. So as you can see, so again, if the total hardness is higher or is larger than alkalinity, then basically the carbonate hardness is going to equal to the alkalinity, right? Whichever is slower. And then the non-carbonate hardness is going to be equal to the total hardness or minus the alkalinity. Okay. So here, let's do a simple example again, so to just get you more familiarized with this process. Okay. So here we have another sample of water that's having a pH of 7.2. It's almost neutral. So on the other hand, you can see that basically it means that the hydrogen and hydroxide concentrations are very low. We can ignore that. So it wants us to calculate what is the total hardness, the carbonate hardness, and the alkalinity of all of these dissolved solids, right? So we want to basically represent these as the equivalent concentration, so basically milligram per liter as calcium carbonate. Okay, so now we can start to construct this bar chart, right, or bar graph, to represent or to find out what is the relationship of these total hardness, carbonate hardness, or non-carbonate hardness, right? So let's again do a table here, right? We have the calcium, right? This is mass concentration, right? We need to find out the Z, basically the number of electrons or number of hydrogen it can accept or release, right? We need to find out what is the equivalent weight. The unit of equivalent weight is gram per equivalent. And then we need to calculate what is the normality. And finally, that's going to be mass concentration as calcium carbonate. Okay, so now we can fill in the spots one by one. All right, so for the calcium, it has a mass concentration of 40 milligram per liter, and Z is equal to 2, right? The equivalent weight is just 40 divided by 2, the molecular mass of the calcium carbonate divided by 2. Put it here. So it is not this 40 divided by 2, but the molecular mass of calcium carbonate divided by 2, right? So the normality will be equal to 40 divided by, which here is going to divide by 20, right? Which is equal to 2. And then the mass as calcium carbonate is just going to be equal to 2 multiplied by 50, right? 50 is the equivalent weight of the calcium carbonate, which is 100 milligram per liter as calcium carbonate, okay? So this is calcium. And then we need to calculate the magnesium. This is 10, it's 2 here, right? And then 24 divided by 2, which is 12. So the normality will be equal to 10 divided by 12, right? And that here, further, we can calculate this is 10 divided by 12 multiplied by 50. And this is going to give us basically, let's see. So basically, we can calculate all of these values after we're done with the calculation, right? Divide by multiply by 50, that is 41.7, okay? And then you can see that basically the sodium is not going to contribute to the hardness, potassium either, right? So now, basically we don't need to build this long relationship here. So we just need to study these two types of ions here, right? And then one thing we need to also worry about is the bicarbonate ion. So the bicarbonate ion has a unit of 61, Z is equal to 1. So the equivalent weight is going to equal to 61. So the normality, okay, so I made a mistake here. So here it should be the concentration. The normality is going to be 110 divided by 61. And that is going to be 61. That is going to be equal to, and multiplied by 50. That is going to be equal to 90.2, right? So now we can start to construct this alkalinity here, or the total hardness here, right? So you can find out, basically build this bar graph. So here, this is calcium. It represents 100, right? And then this section here is the magnesium. This is 41, right? So there can be sodium or potassium, but we don't care about that anymore because they're not contributing to the hardness of the water. Well, for the anion, we find out that for the bicarbonate, it just contributes a little bit, right? It's 90.2. And then the rest of it is actually composed of the other cations, or the other anions, for example, the sulfate or the chloride ions, right? So based on this relationship, you can find out that the total hardness should be equal to 141 milligram per liter, right? And then the carbonate hardness is just the hardness that's contributed by these bicarbonate ion, which is 90.2 milligram per liter, right? And the non-carbonate hardness is just equal to 141 minus 90.2, which is equal to around the 50.8. Okay, so this is an example of how we can calculate the carbonate hardness and non-carbonate hardness, right? And so how do we, since we can already know what is the hardness of water, so how do we treat the hardness, or how do we soften the water? So as I have introduced, we can either introduce, or we can introduce the lime or soda, or lime and soda into the water to treat the hardness, or to soften the water. So this method is called lime soda ash softening. So lime, again, lime is composed of calcium oxide or calcium hydroxide. Okay, this is just a matter of whether they contain water or not. And anyway, if you introduce calcium oxide into water, they're going to convert into calcium hydroxide inside water. And soda, on the other hand, is composed of sodium carbonate in the water. Okay, so the principle of the water treatment with this lime soda method is actually there's a sequence for introducing these different species. What we do is that we'll first introduce lime into the water. So what happens is after we introduce lime, so lime will convert into calcium hydroxide, right? We know that in the water there's always some carbon dioxide, and carbon dioxide can combine with water to form carbonic acid, right? So what the lime does is basically to react with the carbonic acid to form calcium carbonate and to water. Okay, so you can see that it first neutralizes these carbon dioxide from the water, and then it will start to deal with all of those ions in the water. So then it's going to remove these calcium bicarbonate, and the method is that calcium bicarbonate can react with the calcium hydroxide to form two calcium carbonates, and further it converts the magnesium bicarbonate into magnesium carbonate. We have to mention that magnesium carbonate is actually soluble in water, right? So this means that we have to basically convert more. So basically to add more of the calcium hydroxide to remove these magnesium. So basically first what it does is magnesium bicarbonate will react with the calcium hydroxide to form calcium carbonate and the magnesium carbonate. And the magnesium carbonate can further react with the calcium hydroxide to form this solid here. So basically, this will convert all of those carbonate hardness, or the carbonate hardness, into solids. So what happens to those non-carbonate hardness? And for the non-carbonate hardness, what happens is that we have to introduce more carbonate, which is sodium carbonate, to neutralize or to react with, to basically to contribute to these, so basically to contribute to the removal of these species. For example, if the calcium is bonded with the calcium sulfate, and then by introducing the soda into the water, we can form these calcium carbonate. Okay, and also for the magnesium, we can just introduce the calcium hydroxide and form these magnesium hydroxides. Okay, so basically some part of these non-carbonate hardness, if it's resulted from the magnesium, then we can use the still use the lime. But if it's forming these calcium sulfate, then they're going to basically we're going to use soda to remove these hardness or non-carbonate hardness from the water. Okay, so this is a set of reactions that's taking place. Although I introduced them in sequence, but actually in water they just happen everything at the same time, right? And here, basically, this is a brief process of how we can treat the hardness, right? So first, we'll introduce the lime into the water, right? So the lime are going to form these calcium carbonate and magnesium hydroxide, and then after that, we'll introduce the carbonate into the carbon dioxide into the water again, mainly because now the water is really basic, right? Because we introduce a lot of these hydroxide ions, right? So they can further react with the carbon dioxide from the ambient, and then basically to reduce the pH. And then we'll introduce the soda ash to remove the non-carbonate hardness from the water. Okay. So again, you can see that the lime dosage is going to be equal to the carbon dioxide concentration, carbonate hardness, so both the calcium carbonate and magnesium carbonate, and also we need to include the total magnesium hardness. So what happens is that first it will neutralize these magnesium hydroxide, then they're going to react with these hydroxides. So basically we have to double the amount of the magnesium that's in the water. Okay, And in terms of soda ash, that's going to be just the non-carbonate hardness in the water. All right. So this is all about the softening, right? So in basically this is the lime soda softening, right? So we can also use the cation exchange softening. So what happens is that we can use these special types of compounds. So they're going to exchange the cations, and then we can further regenerate these compounds by further processes. So this is in a cycled manner, right? So basically, we're going to introduce this ion exchange resin, right? On this resin, there are a lot of these compounds, so they can exchange the ions, and then we can use this method to reduce the hardness or soften the water. All right. This is how an ion exchange device looks like, right? And I think we can further talk about the sedimentation and filtration in our next class. And feel free to let me know if you have any question. Thank you.